Thanks for being here for Enterprise Do's and Don'ts for AI Infra. Most of our panelists couldn't be here because of flight cancellations, but thank you so much for Uber for showing up. Uber has been the OG for running AI workloads on Kubernetes. They were running it before running AI was cool, and they were running it before running AI on Kubernetes was cool. So I remember my coworker, Ann Holler, who worked at Uber's, mentioning running Michelangelo platform on Kubernetes 10 years ago. So super excited to hear all the wisdom from Uber, especially because the rest of the market doesn't have the time to learn these lessons in the field. So grateful to have Uber. We have Andrew Leung from Uber here to share lessons. Andrew, can you tell us a little bit about yourself and what products that most of us might have used getting to this conference are powered by AI?
Hi. I'm Andrew. I am a lead on the compute platform team at Uber and helping to revamp their GPU stack, which you were mentioning. Uber has been leveraging AI across multiple product aspects for a long time, which is, from an infrastructure standpoint, both an asset and a liability. We have lots of investment there, but we now also have lots of accruing of knowledge of the don'ts as well as the do's. So we're now, much like others, also looking at the community and how we can best leverage the Kubernetes infrastructure and where that's going to also up-level our stack as well.
Awesome. Could you please share some of the products that most of us might have used that are powered by AI Infra?
Yeah, there's a lot of user-facing experiences that are AI-powered. So just going onto the Uber app and calling a ride, the ETAs are powered by predictive AI models. We use that for some of the different offline workloads as well. So anything that after a trip runs, and we do fraud detection and post-processing and things like that of the actual financials, those are all run through models. And then for other products like Uber Eats, it's all very similar. The ranking feed you see of what restaurants and items and things are all from predictive models, as well as then interactions with merchants and things like that. So if you're a storefront owner and you want to start running an ad campaign for something, there's AI tooling that is built there for them to begin to interact and help promote their business.
That's super awesome. Do you run both training, inference, and batch, all three sets of AI workloads, or are you focused primarily on pre-trained models and run inference only?
We focus on both of them. So most of the infrastructure that we run is for predictive models that are powering some aspect of the Uber customer experience. There are now also a variety of LLM-based use cases that are coming around, both for external and internal. So I'd mentioned earlier, if you're a merchant, with a storefront on Uber, there are LLM interactions you can have for how you generate and describe different kinds of aspects for how you want to manage your storefront and things like that. Those comprise both training infrastructure that we run as well as serving infrastructure, and I can dive into those.
Cool. I remember 10 years ago, Uber was one of the earliest adopters of Ray before Ray was super popular. And I know nowadays a lot of people use Ray. So besides Ray, do you run any other AI frameworks, or are you exclusively a Ray shop?
For training, we are almost exclusively a Ray shop. On the training side, the infrastructure is run across our regular batch infrastructure, which also runs Spark and other kinds of internal batch processing workloads. And so a common AI workflow will actually be composed of a number of different steps that can be pre-processing of data, ETL type of workloads, and those things may or may not run through Ray depending on the use case. They could be running on Spark if they're very ETL focused. And then most of the training workloads are all powered via Ray. And then on our serving stack, the serving stack is powered generally through either NVIDIA Triton as our key model serving engine for our predictive models, and then leveraging an increasing amount of VLLM for some of our more internal LLM-focused use cases.
Super cool. So getting down to the infrastructure, we are at KubeCon and we're all Kubernetes fans. So can you please share which parts of the training inference batch stacks run on Kubernetes? And if you're not using Kubernetes, why not?
Yeah, so I can give you a little bit of background about Uber's infrastructure evolution. Circa 10 years ago, all of the compute infrastructure was run through an in-house built Mesos-based container platform, and Uber has spent the past 3 or so years doing a large wholesale migration of all of the infrastructure from that to being run natively on Kubernetes. Now that we've completed that migration, a lot of the focus is on how we improve our leverage and make use of best practices that are now available to us. In our migration from our existing stack to our new Kubernetes stack, we pulled forward a pattern we had where we had dedicated batch-focused infrastructure, as well as having microservice-focused infrastructure. And so in doing so, we ended up with a Kubernetes infrastructure focused on batch and a Kubernetes infrastructure focused on microservices. And I'll make a distinction here that they are at the workload level, not necessarily just at the GPU training level. So a lot of the batch infrastructure that we build supports both what we do for training as well as Spark and general batch use cases. And the same goes for our inference services. They're generally run and handled much like other internal microservices at the company. So the same tooling you would use to deploy an internal microservice would be the same tooling you would use to deploy your inference services.
Thank you. Do you run both non-AI microservices as well as AI microservices for training, inference, and batch? Do you run them on, do they share the same clusters, or do you have separate silo environments for AI and non-AI workloads?
In general, the distinction, and this is one that we're actively trying to evolve right now, the distinction has been that the hardware was segregated at the cluster level. So we would have dedicated GPU clusters that were just serving GPU workloads and a number of CPU-based clusters serving CPU workloads. Each of these were actually comprised of multiple clusters underneath that were segregated over different fault domains and things like that. But that's led to siloing of the actual capacity and ends up sort of over-indexing on a Kubernetes cluster as an abstraction for hardware rather than leveraging a lot of what we can do internally from Kubernetes itself. So we are also looking at how we can better reorganize kind of how we're creating and mapping hardware to clusters. And that's true both on the serving and training side. We have clusters on the training side that are handling both GPU and CPU use cases, but there's a lot of up-leveling to do there as well.
Interesting. So does that mean that your training, serving, and batch infra is segregated as well, and you don't share infra across training, batch, and serving?
That's correct. I'd mentioned earlier we have infrastructure for hosting microservices. That infrastructure is what's hosting our inference serving services, and that's a separate set of clusters than we have for leveraging our training infrastructure.
Cool. So earlier we were mostly running, if I remember from 10 years ago, Uber was mostly running on on-prem data centers, and now we have the public cloud and a lot of neocloud providers. So what are your thoughts on sourcing your GPU clusters as far as you could share with the audience?
Yeah, I guess a little bit of background also. As you mentioned, Uber was originally built all on on-prem data centers. We are now in a move from our on-prem data centers into the cloud and actually going with a multi-cloud strategy, which has both positive and negatives to it. There are aspects of leverage we can get from being in multi-cloud, but there's also drawbacks you have in trying to manage multiple cloud providers. So one of the things that affects our internal infrastructure and then how we put together our Kubernetes stacks is how our data and compute can be separated. So we have data lake that's running in one cloud provider where we felt like that was a strength from that cloud provider. And then we have a lot of inference and other microservices running in another cloud provider where we felt like that was a strength we could leverage that cloud provider for. But while both of those things let us optimize those areas specifically, it now makes it more difficult to build converged infrastructure because we have this cloud provider divide between there. And so we end up with infrastructure that runs in one cloud provider for one use case and for others. And we want to get better at how we can cross that divide, but it ends up becoming an interesting calculation of when it makes business sense to do that, particularly for GPUs and GPU capacity. It's scarce for us, it's expensive for us, and so we want to make sure when we actually have it available, we can leverage it as best as we can. And that becomes difficult when it might be in a different cloud provider, and we might need to move data around. And so we end up having to think about use cases that can either reside entirely within one cloud provider so that I can put training and serving together, or I need to think about the use cases where it makes sense to actually pull the data from one provider to another in order to facilitate being able to leverage that compute. And so it doesn't make it quite as seamless as it could be, and you have to be purposeful in how you think about what workloads you're going to be converging together.
Interesting. So if I hear you right, you're saying that each silo cloud provider, the workloads are special pets. So there is no seamless workload transfer across cloud providers as of today. But within a single cloud provider, how are you looking at your cluster management? Do you have workloads being scheduled to individual clusters that are pets, or are you looking at your cluster fleet as a single source of compute that your workloads can automatically be shipped to any cluster?
Yeah, it's much more the latter. Most of the way we structure our Kubernetes clusters is that they just become a fault domain and are generally tied to our internal architecture. So if we're splitting across a cloud provider who's giving us N zones and M regions, that will become kind of the granularity at which we end up segmenting Kubernetes clusters. And then how we disperse workloads across that is usually just with the notion of first being able to satisfy whatever fault requirements the application has, so spreading sufficiently, as well as then the second order piece is to leverage available capacity as best we can. And for CPU workloads, this works generally well. It's a very well-worn path. For GPU workloads, it's much less so, both from a where is capacity available and the fact that we have so many new use cases coming up in this space. And so one of the common patterns we have is thinking about, fallbacks and things like that if a model can't be available because of something else like that. And so it provides new layers of complexity to that area.
Thanks for sharing. Over the last couple of weeks, we've seen two regions across two major cloud providers go down. As people start to think about building their enterprise AI workflows, would you be open to sharing the practices you have in place for disaster recovery that the audience could learn from?
Yeah, I think a lot of patterns exist for our normal, product level microservices. So, for instance, if a US East 1 goes down, being able to do a region failover and have at least the product not be affected by that, so the end user experience isn't degraded. But that all becomes increasingly complex for GPU infrastructure, given the cost and scarcity of it. So in a lot of cases for this disaster recovery, we're pre-planning the capacity and how we end up architecting how services scale, how we do overcommit on certain resources, and things like that to ensure that we have all of the pieces in place so we can just push a button and evacuate a zone or a region. That's much harder to stomach when you see how much extra overhead you need to carry for GPU, and also given the fact that GPU workloads aren't quite as fungible as CPU workloads, where I can't as easily just dynamically pack 8 workloads onto one GPU now, where I could have just squeezed things onto a single CPU. And same thing for, serving, where this thing is optimized for this particular hardware with this particular configuration. If I do a failover, I can't necessarily easily just move it to a different hardware configuration on the fly. So it requires a lot more forethought there in how you need to think about that. And I don't think, it's something we're continually working through. I don't know that we have a obviously solved solution to it. One of the aspects is to where it makes sense for the main critical services to be able to do that and be purposeful about it. In other cases, we have AI workflows where we know we can fall back to a good default and may not need the same level of disaster recovery scaling that we use for other things. So you end up having to get a little bit creative there.
Interesting. A lot of the ecosystem folks are starting to think about distributed training and distributed inference that stretches across clusters, not limited to a single cluster. So do you guys stretch your Ray framework across multiple clusters for disaster recovery or for better SLAs for the enterprise users?
Yeah, so we have the Ray infrastructure spans across multiple Kubernetes clusters. So in general, if you're kicking off a ML pipeline, you are in all likelihood running across several distinct Kubernetes clusters underneath. Often that's for some mix of load balancing and capacity availability. But we're just starting to get into an area where we're actually doing distributed training across with inter-GPU communication. A lot of the previous models that we've been building, since we've had them for a long time, were built for older hardware, and they're not nearly as big as something like an LLM type of model. So they were able to be run intra-GPU fairly well, and we're now beginning to start to see cases where we want to do larger scale training, which is also causing us to step into that. And so I think that's an area where, as we step into that, we begin to look at the Kubernetes community for the best practices there. So we've been just recently standing up our first Rocky-based RDMA configurations for some internode training, and then looking at mechanisms for how we expose those, what best practices for exposing those as resources, and how that integrates with Ray and those kinds of things.
Interesting. Would you recommend having a large number of small clusters or a small number of large clusters? And could you answer this question for training, inference, and batch?
Yeah, I think, at least in my mind, what's maybe more important than the distinct size of the cluster is the meaning of the cluster itself. A lot of, I was mentioning earlier, we had use cases where clusters were sort of tied to hardware and had more of a semantic meaning, and that was problematic from a number of different areas. And we've been on a path to move towards the cluster just becoming a scaling unit. And so whether it's big or small, it's really just that there's no necessarily distinct notion of the special purpose of this one cluster. Rather, I can have this cluster as a unit that allows me to horizontally scale my compute infrastructure with a way where I can aggregate above that and see the entire pool in a way that is largely cluster agnostic in that way. And so that's another place where, things like Kubernetes, DRA are things that we're beginning to look at there. And so in this siloed world where we do have specific hardware tied to specific clusters, it then leads to size asymmetry, which whether they're all big or they're all small, you could make a case for either, I think, but certainly asymmetry between them is a challenge. And one of the cases is just operational configuration, where whether it's an alert or some monitoring you have set up, it has some assumptions about an approximate size for configuring thresholds and things like that. And if you have clusters of 5,000 nodes and of 50 nodes, it can be difficult to mix those things together.
Interesting. Talking about logging, monitoring, and analytics, most of the folks in this room would have a lot of experience running enterprise workloads on regular clusters, regular enterprise workloads. When they're starting to look at deploying production quality AI workloads, AI workloads fundamentally have different SLA requirements from non-AI microservices. So could you please share some of the gotchas or some of the things that people need to keep in mind for enterprise readiness, for training, inference, and batch as well?
I think one of the things that we've just kind of recently learned and begun investing in recently was on our serving stack, what we were actually asking each serving instance to be doing. And we found that in a lot of cases, the GPU utilization we were getting out of our serving instances was not nearly as high as it could be. And a big portion of that led to the amount of non-GPU essential work that was happening there. So some of the pre-fill and decode and other auth-related steps to just responding to a request are not necessarily needing GPU. And so we made a architectural split at at our serving layer, where we now have kind of a disaggregated setup where there's services running in our CPU clusters that are handling these parts of the query request, while the GPUs are handling the very GPU specific aspects of handling the model queries. And so that was able to both improve our overall performance from every single instance, because we were actually able to optimize CPU and GPU distinctly, and it then shrunk the GPU footprint considerably, which boosted the utilization of each instance while making a bunch of other GPU instances now available for other use cases.
That's super insightful. In addition to that, did you have any observability or logging, monitoring, and analytics gotchas or things that people need to keep in mind for AI workloads?
Yeah, one of the, I guess, downsides of being early in the AI space is we had a bunch of GPU infrastructure that was stood up in 2018 or so, for example. And as we've been revamping the stack, we've been up-leveling and modernizing that. And we had to go through a large, just metrics level migration as we moved from our older GPU metrics, which were based around C-Advisor and had a number of drawbacks with just not supporting newer models or C Group v2 or a bunch of different aspects. And so that then caused us to think about the durability of our metrics. What had happened is we'd advertise these low-level metrics, which then other teams began building their dashboards and metrics and systems around. And then when we think about, okay, we want to actually migrate this to a different metric set, well, the whole company is pinned to this small set of metrics, how do we do that? And that problem is for us becoming increasingly wide because we have NVIDIA, we moved to their DCGM native metrics, but we're also looking at AMD, and they have ROCm specific metrics that they're exporting. And if you think about, you're also running on TPUs or AWS or some other specialized accelerators, you're going to end up with a mix of a variety of different metrics and with nuances about what each of them means and how teams should understand it when they're trying to think about high-level utilization or cost efficiency or memory usage. And so what we've been doing there is trying to build metrics almost as an API where we have specific platform metrics that we're exposing, which we can then potentially source from a different level of different variety of vendor-specific metrics, but that it doesn't require the user to have to be as deeply entrenched in any one specific vendor's model metrics. And then it means that on the platform side, we can shift things around more easily. And so if we introduce whatever some new accelerator down the road is, we don't have to do any large migration or re-educate the whole company.
Super insightful. Thanks for sharing. There must be a lot of vendors in this room that are building products in the AI ecosystem. Would you have one piece of advice to folks from the vendor ecosystem as to, hey, we folks are trying to solve this set of problems, and this is a other set of problems that are a good set of problems for vendor ecosystem to think about?
Yeah, I think one of the challenges I was just alluding to before that we're facing now is a diversity of accelerators and runtime environments. So as we've been increasing our GPU footprint, we've been bumping up against cases where in certain zones or regions, our cloud providers don't have either certain capacity or the certain models that we need. And so that's forcing us to go and look for alternatives, both to de-risk supply and enable us to get cards faster, as well as potentially becoming a cost lever. But it exposes all of the areas where you made some decisions several years ago that's just now married to some NVIDIA thing somewhere, and thinking about, okay, now I need to actually be able to move my workloads around to both different providers. Maybe I'm running in a neocloud or on-prem or in a hyperscaler, but I want to make that fungible to the end user. But then also a stack where I can actually move my workloads between different accelerator types. And that's particularly difficult because they're often so tied to specific models. And so some things that we're looking at as first steps is like decomposing images, container images, so that we can have things like CUDA as a sidecar, ROCm as a sidecar, as opposed to what we've been doing, which is just bake it into one giant mega image. And so I think for most companies getting into that space, it's a likely scenario that you're going to have to think about how you diversify your GPU and GPU provider portfolio. And so I think will be a relevant challenge for folks going forward.
That's super insightful guidance. Thank you for sharing. Do you have one piece of advice as a takeaway for the end users, enterprise users that are starting to build out their training, inference, and batch stacks that they can learn from Uber?
Yeah, I think one of the, well, I don't know if I would quite call it a don't, but it has challenges to it, is thinking about where your data lake sits relative to your serving stack. So an ideal situation is one where I could imagine having all of my training and all of my serving being able to leverage the same hardware. I can optimize around this one hardware, and I can preempt training to facilitate scale-ups or failovers or what have you. But that's difficult to achieve in a lot of cases from the amount of data that you have, the mix of workloads and hardware types that you have. And so, but it gets to the idea of the GPU as a unit becoming more fungible than it is today, and being able to, in real time, make a utility decision of what's the best thing to do with this particular GPU. And the closer you can bring your infrastructure together from a data and compute, and how you segment clusters, how you route across them, all become big levers for how you can enable that. It's still not an easy problem for sure, but those are some key building blocks that will help enable it.
That's super insightful to hear. I was excited to see the Tinker API being released last week at Array Summit. That kind of alludes to the AI framework that is a combined framework for training and inference as well as people like me who are working in the multi-cluster ecosystem. We are looking at commoditizing clusters. So it's kind of like that's where we are heading to as an ecosystem.
Yeah, I mean, I would be interested to hear from your perspective, looking across other vendors with similar problems. Do these things resonate? Do they have different challenges that they're focusing on?
You guys are the North Star for us. So you're the ones that give the problems and the vendor ecosystem solves it. So for sure, we've been thinking about multi-cluster for many years, and AI has been the trigger for multi-cluster to be a reality because GPUs are scarce and expensive, and also there are too many kinds of GPUs from various vendors and too many cloud providers. So that's an area that we are excited about. So it's great to hear from the enterprise power user that it's actually a problem, today's problem, and it's not a theoretical, nice to solve problem in the future.
Yeah, I think one of the things that we're looking for from community and to see where it evolves is some best practices for managing across multiple clusters. I think from both Uber and experiences I have from previous places and colleagues, I know it's a mix of different patterns and things that are all largely trying to get at the same problem of being able to get fault tolerance, cost efficiencies, and things like that out of these clusters. But they're often done in different ways, and so things like queue and multi-queue are interesting things that we're exploring and trying to get a better sense of federation and common patterns around that.
Awesome, thank you. And thanks so much, you all, for joining our session. I do want to give you a chance to ask Andrew questions, so we are opening up to the floor.
Yep. We've got a microphone over here if you want to queue up questions. I can.
Thanks for sharing insightful and practical conversation. We are in the same journey, like managing hundreds of clusters. But thanks for sharing all the details. But I have a few questions related to some of the things that you mentioned about training and inference, right? So are you building your own models, or you're just fine-tuning the existing models?
For our predictive models, they're all our own models that we've been building for a long time, and they're very narrowly focused. So, they're ones that are built to produce the feed ranking for your Uber Eats experience or something like that. We have a growing cases internally where we're building and doing fine-tuning on existing models. So there's a number of internal initiatives around building agentic systems for all of our internal tools and providing mechanisms where we have LLM-based support for different internal systems. Those are often then taking an existing model and providing some layer of fine-tuning on top of that to then produce something consumable and useful to an end user. But relative to the GPU infrastructure, that's still the minority of things. But as we increase investment there, has the potential to become larger scale. The predictive models that we've been training aren't likely to double in size, for example, because they just generally grow along with business growth. But the use cases internally, you could just say, wow, we've unlocked some major agentic workflow, and now we're going to put it everywhere, and then that would be a huge increase in what we need to support there.
Yeah, that really helps because predictive models existed before GenAI, right? So yeah, definitely, it makes sense. And I have a few follow-up questions on some of the things that you mentioned about whether to have small clusters like versus like having large clusters, right? So how do you see the utilization in terms of whether it's CPU or GPU workloads?
Yeah, I think all things being equal, a large cluster is a easier construct to work with. And if the cluster is just a scaling unit, then it's both just serving as scaling and some level of fault domain.
Okay.
And so if you can have as few of those as necessary is beneficial, both from an operational perspective as well as enabling easier access to a more optimal bin packing strategy or something like that.
Okay.
However, practically speaking, I think it's not always doable, and it's not like, a cluster that's 1,000 nodes is some terrible anti-pattern or anything. What I was mentioning before, I think some of the mixes of very large and very small clusters can be problematic, and then maybe some of the egregiously small clusters, which we've unfortunately had some examples of, are themselves an issue. One node goes away, and I've lost some huge fraction of capacity is a challenge.
Yeah, we can get that conversation going in the hallway. We can wrap up with some quick questions if you have.
Okay. So I wanted to ask about your fungibility story. Not all GPUs are made equal. They have different GPU memory, different even architecture with the new GB200 coming up. So you mentioned something around sidecars, but then with GPUs everything being vertically integrated, how would you manage that? Especially one application being CUDA compatible, while other not being, AMD doesn't have CUDA. So what's the?
Yeah, I think it's a very much unsolved problem for us as well. How some of our models will get set up is we'll end up with, building the model, and then they'll get shipped as, we'll use TensorRT, and you get hardware-specific optimization on this model for this particular thing, and then we're mapping it to the whatever the Onyx runtime that we're going to then ship off to actually run. And so today, with how we have clusters set up, the cluster is the boundary, and so we're moving away from the cluster as kind of its own silo there to help make that more fungible as a first step. So I can say today, if I have H100s and some 2G MIG configuration, they might be scattered across clusters. Today, you end up getting siloed in one cluster and can't necessarily optimize that. So the first piece of fungibility we're trying to do is break down that wall between the cluster boundary. And that's up-leveling some of the abstractions that we have, like you were describing, and going across clusters. The next step will be the actual runtime pieces, and that will be, I mentioned before, we did some work around disaggregating CPU compute and other pieces. And I don't know the extent to which we'll be able to pull out huge pieces, but to the degree that we can make as much of the runtime pieces dynamic late binding kind of aspects, where I say, okay, now I know that I'm going to be placed on this kind of card with this kind of configuration. Now pull the best configuration at that point, as opposed to baking it in a priori. So it remains to be seen how much we can get out of that, but that's kind of the lever there that we're looking at.
Can we take one more question?
Last quick question, sorry.
Okay, great, thank you. I just had a question about agentic workflows. You mentioned it at the very end. And what I've been learning is those really need to be verified when you have them in production. And that requires a significant level of compute to do that. So I'm thinking about that in terms of what you're talking about, your GPU infrastructure, and how you think about your architecture.
Yeah, that's a good point. I think it plays a real factor in what we do today, often from a cost efficiency perspective, because a lot of our investments in those kinds of agentic workflows are often experimental, but still require a non-trivial footprint. And as an experimental product, they're not in production necessarily, so they're not taking constant, always-on high volumes of traffic, which makes it suspect as to whether or not the end GPUs we provision for this thing is really the best use of them. And so that's an area we're looking at now. Some of the things that we're investing in is making our GPU infrastructure more elastic, so increasing our ability to auto-scale these services with high fidelity, as well as auto-scale the underlying clusters, where we can say, okay, this workflow is low utilization right now. We can scale in that service, reap these GPUs, and potentially repurpose them for something else. But I think will become an increasing challenge as more and more use cases come on, and we have to balance the speed of innovation internally with those things versus the operational costs to power them.
Thanks.
Thank you, Madhuri and Andrew. That was a really good discussion.